We are looking at the power series today. So looking at approximating different functions with the series. Okay, so going to look at a Desmos calculator. So I've got it set up where I'm going to graph f of x equals e to the x, and then a polynomial function represented by this series here. So from n equals 0 to a, we're going to start with a equals 2 and look at what happens as a goes from 2 to 10. So as we increase the number of terms of that series. So I think you can see all of it there. So the red graph is your e to the x exponential function. So the blue graph is the series. So we're starting at going from n equals 0 to a. So basically 3 terms at those particular x values. And you can see around the value of x equals 0, the graphs look identical, just around that y-axis. Now, as I'm going to set this to increase from 2 to 10, let's see what happens. Okay, so you can see that it's flipping on the negative side. Now it's going back and forth, but as the number of terms increases, the blue graph approaches exactly the red graph for much of it. Certainly for anything sort of greater than -3 there. Okay, so it's a great approximation. And so using series to approximate functions is really helpful, particularly I think in programming. A lot easier to use a polynomial function if you can, as opposed to an exponential or a trig or stuff like that. So it's just, that's what we're looking at, how to approximate certain series, certain functions with a series. So take a look back. That's what we just graphed. So the series defined here, okay, so it's a series that converges for x element of reals, and it converges to that function that we compared it to, e to the x. Okay, so it's approaching e to the x. If the partial sums of a series have a sum, okay, then each of these, so take a look here, S1, so this is good review of series from Math 30 and 20, I think. Okay, so it's going to make this a little bit thinner. So S1 is the same as the first term. So here the terms are using A's. Remember, you could use T's or U's. In this one, we're using A's. S2 is A1 plus A2. S3 is A1 plus A2 plus A3. And so on. So sometimes we show in the general case here, obviously going to A to the AN. This just means that K is less than N. So sometimes we want to stop it at a certain value, but that really is the sum of the series, Sn. Okay, so you can see if these start approaching a certain value, that means the last term is getting smaller and smaller and smaller, right? So that it's not making a difference as you keep adding the next one. So if the limit of S sub k, as k goes to infinity, equals L, so where Sk represents the kth partial sum, then the series converges to L and is said to have a sum. All right. If the series did not converge, then it diverges. All right. So if the series represented here converges. As I just said, the limit of that last term, okay? So if k is going to infinity, that limit of the last term has to equal 0 if that series converges, okay? But that doesn't guarantee that it does. So if the limit of the last term, so as k goes to infinity, equals 0, then we say there's a possibility that the series converges, okay? If you find that it converges, then for sure the limit of the last term will be 0, but the other way, what's just written there, isn't guaranteed. And you can kind of think about it. If you had a series, like I mentioned yesterday when we were doing the limit of, we were doing the integral of 1 over x dx, and so the area did not converge. So if this was some kind of series where we had 1 over x, yes, the last term converges, the last term goes to 0, but the whole series won't. So power series, a well-known power series is this one, because you've actually already done it. So geometric series is actually a power series, okay? So this is a geometric series and converges if the x value is less than 1 or greater than -1, right? So back, we didn't call it x when we were doing series and sequences, we called it r, the common ratio, what you keep multiplying, because you can see here that you keep multiplying by x because your index is the exponent on x. Okay, so remember infinite series. So the sum of an infinite geometric series back from Math 20 was the first term over 1 minus r. Okay, in this case, the first term when n equals 1 would be a. So a is the first term. So this is going to converge to a over 1 minus r. Okay, so definition of a power series. So it has to be in this expression here so that we do have a common ratio. So some constant, okay, that constant can keep changing. So n, 0, and 1, etc. Okay, but you keep multiplying by x. Okay, and then expression of, so that's considered centered at x equals 0. If this is x minus a, then it's centered at x equals a. It means it's going to be more accurate at x equals a for smaller numbers of terms. Okay, so let's do some examples here. So there is your basic geometric infinite series. And so we know, so here the common ratio is x. So, and the first term is 1. So there's your sum of that series. So we know that if r is x, then remember r has to be less than 1, greater than -1. So what do we do here? If we have this, it's very similar, except x is the opposite sign. So all we have to do is replace. So here, this is equal to 1 over 1 minus -x. Just a sec here. Okay, so that means we just need to replace the x in our original with -x. So the series will equal the sum from n equals 0 to infinity of -x to the n. Okay, so what's that going to look like? So it's going to be 1 plus -x plus -x squared plus -x to the n etc. So then just simplify that a little bit. So basically you can see the signs alternate. The next one would be minus. And then we'll leave that as negative x to the n because we don't know what n is. It's even or odd. Okay, so the signs there will alternate. And you can see that if we replace x here with negative x, so we know that x has to be between 1 and negative 1 in the given. So this has to occur. So remember, when you divide by negative, you're just changing the changing the direction. So that'll change. You're dividing everything by negative 1. And so it still works out the same. Okay. So the only difference here is that this is x times 1 over 1 plus x. And we just already figured this out. This is your previous. Okay. So the series will equal x times that series from the one above. Okay, we already figured that out, so that's 1 minus x plus x squared minus plus negative x to the n. Okay, and then just multiply through, so that'll be x minus x squared plus x cubed. Again, a minus, and this will be negative x to the n plus 1. Brackets anymore. Okay, if you want to show this sort of in a simplified summation form, then so here this would equal basically x times negative x to the n. This here is negative 1 to the n times x to the n. So then we can simplify the x's. So that would be negative 1 to the n, x to the n plus 1. So it's basically just multiplying this x in with x to the n. Okay, so that's how you could show that one. Okay. And again, this will stay the same because we already figured it out from there. This one, this is really 1 minus now 2x. So that's your r is 2x. So your series and so now we've got 2x to the n. Okay, so it's going to be 1 plus 2x plus 2x squared plus 2x cubed. Oops. Okay, and then you can simplify that. Should have actually put that underneath. Let's see. 1 second here. That's better. Not two equal signs on the same line. So then just expand the brackets. I would need that one in brackets like that. Okay, so in this case, think about it. Your common ratio is 2x. That has to be less than 1, greater than negative 1. And that's why if we divide everything by 2, we get this. So just so you know where that's coming from. Okay, so this one we've given you a hint. So this is now your r, because if we simplify this, we get 1 minus 1 is 0, minus a negative x is a positive x, right? So those are the same. So this is your R, okay, common ratio. And so that's really goes into your series. And equals 0 to infinity of that 1 minus x to the n. So first term is 1 plus 1 minus x plus 1 minus x squared, 1 minus x cubed, 1 minus x to the n, etc. And then in terms of this, what it's defined for, your common ratio has to be less than 1, greater than negative 1. So now your common ratio is 1 minus x. So we want to get rid of the 1. So that would be negative 2. So subtract 1 from both sides. Divide by negative, so that would be positive, and your direction of your inequalities changes. And so that's the same as that. Then 1 over 3x is really, so the hint again here, we just found this in the previous, and it's just 1/3, okay? In terms of filling this part in, so now this is going to be exactly the same as the last one, because multiplying this by 1/3 doesn't change the common ratio. So this is still going to be between 0 and 2, as we calculated there. Okay, so our series is just going to be 1/3 the series that we just determined above. Many terms here. Okay, so 1/3. And that's your series. Okay? So those are all based on the geometric series. Okay, x to the n. So nothing else was in with that. That's a basic geometric series where your common ratio is x. Okay, and so using your definition of the infinite sum, 1 over 1, sorry, first term over 1 minus the common ratio. Okay. All right. Now, if we had started at a different n value, then your first term wouldn't be 1, right? But these usually start at n equals 0. Okay, so here's another series, interval of convergence for this function here. Okay, so what's changing? Think about what you're multiplying each time if you were to find all of the terms. So if we were to write out the first term, when n equals 0, that makes this x plus 2 bracket equal 1, so that would be 1/3. Then plus n equals 1, so that would be 1/3 times x plus 2, and then plus 1/3 times x plus 2 squared, etc. Okay. So our common ratio here is x plus 2. That'll be less than 1, greater than negative 1. So we subtract 2 from both. Okay, so we get that as your, so R equals x plus 2. And then this is your interval of convergence. And then the function generated by this, okay, so let's think about, it is a geometric. So our first term, so our function, we can call it y equals, okay, it's going to equal the sum of the infinite series. So the first term is 1/3. 1 minus, the common ratio is x plus 2. Okay, so really the 3 can go down below, and then we'll have negative x minus 1. Don't really like keeping negatives there, so I'm going to factor out a negative, so that's x plus 1. So I'm going to put that out front. So negative 1 over 3 times x plus 1. Okay, so that is your function generated by that series. Okay. And then the next one, using differentiation to find a series. So we already know, there's your basic geometric series. Okay, so what about if we take the derivative of both sides? Okay, because those are equal. So if we take the derivative of both sides, they will be equal. So the derivative of 1 over 1 minus x. Well, I'm just going to show that as 1 minus x to the negative 1. Okay, so now derivative of that is going to be negative 1 minus x to the negative 2. And then multiply by negative 1, chain rule on the inside, equals derivative of the right side. So derivative of 1 is 0, derivative of x is 1, plus 2x. Next would be 3x squared, nx to the n minus 1. Okay, and so let's simplify this a little bit. A negative 1 times negative 1 is positive. So that's going to be 1 over 1 minus x squared. So that is now the function that approximates this series. Okay, in terms of what x has to be, so back from the top, we know that x has to be less than 1, greater than negative 1 for that to work. Okay, so it's not going to work for all x values, but it will work for those. And then we can also use integration of this. So again, based on your basic geometric series there, okay, I'm going to change it to t's just so that we can integrate with respect to x. So the last one, we differentiated both sides. Now we're going to integrate both sides. Okay, so this is going to be, you might want to let u equal 1 minus, integral of 1 over u is ln u, which is u is 1 minus t, the absolute values for now. And that's going to be a negative out front because of that substitution. We're going from 0 to x. Integrate each term here. So that's going to be t plus t squared over 2 plus t cubed over 3 plus t to the n plus 1 over n plus 1. And then from 0 to x. Okay. And then substituting in here, negative. Now, x is going to be bigger than 0. Yeah, so we need the absolute values. So ln of 1 minus x minus, so you're subtracting a negative, so that's going to be adding ln of 1 minus 0, which is 1, which is actually going to be 0. Equals t plus t squared over 2 plus t cubed over 3. Oh, that's substituting. Sorry. That's going to be x plus x squared over 2 plus x cubed over 3 plus x cubed plus 1 over n plus 1. And then subtracting 0. Now, if we divide everything by negative 1, we'll have ln of
1 minus x equals negative x minus x squared over 2 minus x cubed over 3 minus x n plus 1 over n plus 1. Okay, I guess you could show this as ln of 1 over 1 minus x because of the negative, but this will be more often how it's shown. Now remember that in this case, x has to be less than 1, greater than negative 1. So if we think about that, if x is less than 1, this will never be negative, so we don't need the absolute value signs. Okay, so there's another approximation of ln of 1 minus x. That's what this series approaches. Okay, or vice versa, you can show ln of 1 minus x as this series. Okay, so those are some power series.